Hello and welcome back to Calculus 1. This is section 5.5 on U substitution, which is probably the most frequent, most used integration technique in all of Calculus 1 and Calculus 2 and Calculus 3 and differential equations and so on. So U substitution is one of the most common and most frequent, and the reason is that it is backwards chain rule, and we know that the chain rule is one of the most frequent differentiation techniques. Therefore, the opposite of chain rule, which is U substitution, would be something that would be also most frequent and most useful. As I mentioned before, there is absolutely no calculus 2 without this method, so you really have to know it well. And usually I do this in two parts, right? Part 1, part 2, so that we can stretch it throughout the entire week and think about it and work it a lot. Let's go and start with the idea that we have an integral that cannot be solved using the regular antiderivative charts. So we learned let me just jump real quick, in 4.9, right, that we have these basic integrals, and we called antiderivatives. Let's just go up a little bit somewhere. And I just want to find one formula that we said. There we go. So all of these are all basic chart, right? And you can, for instance, see right here e to the x, right, or sine x, and so on. Now, some of these problems are going to be more involved. So some integrals, let's say you can have integral on 2x plus 3 raised to the 6th power dx. Right, and when you look at this integral, you would say, well, if I FOIL this, right, to the 6th power, meaning write these out 6 times and multiply them all, right, and good luck with that calculation, you can solve it, but it's going to take a long time. Is there a faster method that would obviously work in some situations? And the answer is yes. So we go and we say, and this is something that will be happening in your head. I know that the integral of x to the 6 dx is x to the 7 over 7 plus c. But you don't have x to the 6. You have this whole mess raised to the 6. So if I could just somehow swap that out, maybe I could, right, have this easier to solve. So you know what I'm going to do? I'm going to say u equals 2x plus 3, just because I can. And I also need this dx to replace it, because I can't have u to the 6 dx. Then the variables dimensions don't match. I am doing the transformation now, and I'm moving from x domain into u domain. So if my function is going to be in terms of u, my dx also better be du. So if I differentiate this one, I'm just going to get 2. And then I can write it as du equals 2 dx, from where I can see that if I want to replace dx is du over 2. So all of this here is a transformation which we call u substitution, because I am replacing now 2x plus 3. I am replacing that by u. There is still a 6th power. and the dx is replaced by du over 2. Now you can kick that 1/2 in front of the integral. We know that about our constants. And look, your integral now is fully transformed into something that you can easily solve because you know what the integral is. So what I used here is the fact that I can swap that in, and let's say this green or whatever, this guy is right there. And those are your old, right? So you can see the way they're all connected. And now this problem becomes a very easy problem to solve. Oops. This becomes a very easy problem to solve. I have 1/2 in front, and then u to the 7 over 7 plus c. Now that's what we know from before, right? That x to the 6 goes into this. That's a basic one. So technically what I have is u to the 7 divided by 14 plus c. Now, we are not allowed to leave the answer in terms of u, because u is a transformation. U is transformation, and we need x. So now we have to plug back what u is to transform it back into x domain, and that it's 2x plus 3. We still have the 7 and then plus c. And the problem is done at this point. So as you can see, we transformed from x domain into u domain. We solved it in the u domain and then went back to x domain. So we just use this idea of u substitution to simplify the problem so it's easy for us to solve it. So technically, if you want to check this, you would have to use chain rule, because I mentioned earlier that u substitution is backwards chain rule. So the check procedure is to differentiate this answer. And that is equal to 1 over 14, that's the constant, then differentiate the top, which will give you 7 times 2x plus 3 to the 6th power times the chain rule. Derivative of the inside is 2, plus derivative of c is 0. And now when you see that you have these guys canceling, because 2 times 7 is 14, divided by 14 is 0, is 1, sorry, 14 divided by 14 is 1, you get your 2x plus 3 raised to the power of 6, which is actually what we had as our problem. And you can see that we had to use chain rule, right, to take the derivative. So is it possible for us to write some kind of formula, which we will never use, for u sub? And the answer is yes, but no one ever uses the formula because it's just ridiculous formula. We can construct that formula easily by writing down that the derivative of f of g of x, right, which is the chain rule, is equal to f prime of g of x times g prime of x. And now, looking at this formula, we see what we need for the u substitution, and we can, right, we're looking at the chain rule, we can construct the formula for u sub, but as I said, you will never use the formula for u sub because you are supposed to, well, I'll show you the technique actually that it's used, which makes it easy. Right now, this is just too much. So technically, what you want to have is you want to have the integral of f prime of g of x times g prime of x dx equal to f of g of x, right? So that's, and then there will be obviously plus c in the. So technically, right, this is your formula, but we don't need this prime here, right? We don't need this prime. So moving it without the prime, it will be like f of u times u prime dx is equal to f of u plus c. And then looking at this antiderivative here, this would be your du technically. So it simplifies, but it, again, no one ever uses this because it is just, it doesn't paint the picture, right, of what we actually have. And from this step to this step, we made this u equal g of x, which is technically what we had up there when I said u equals 2x plus 3 or whatever we had, right? That's what that step happened. So this would eventually be f of g of x plus c. And in some sense, this is the formula for u sub, which, as I said, we never use. I will show you the really cool way of dealing with the u sub. So let's go and take a look at ways. Again, simple cases first. Whether you wrote this or you didn't write it, it really doesn't matter. I mean, you can go back in a YouTube video and just, look over it. But let's take a look at the procedure, right, of this. So let's say that you have this very simple integral, and you probably memorized this back in 4.9 when I told you what it is. But now we can actually compute it. And it's done by saying, oh, what I know, see, this is, every time I write this in orange over here, is I know that the integral of e to the x dx is equal to e to the x plus c. Like that's what I know. And when I compare the two problems, you can clearly see that the difference is this one and this one, right? That's the difference. So I have this difference, and this is how I say, okay, let u be 3x, and then du, well, let's u be 3x. And if I make this, substitution, I will get integral e to the u, and I am already in this mode here. I'm already in this mode where I have e to the x, which is the basic thing that I know. So we have now, all we need to do is to transform this dx, and we will be done with the whole problem. So I go here and I differentiate, because I will get du over dx when I write it in Leibniz notation. The derivative of 3x is just 3. And then that transforms into du equals 3 dx. And as soon as you have this, you can solve it for dx. as a du over 3, and we get du over 3 in here. So now we kick this out, and there we go. There we go. We have 1/3. Now the derivative of e to the u is e to the u plus c. And we just bring back like e to the 3x because u is 3x. We can put that back. And we technically did all of the steps in that calculation which you previously memorized as the formula. Right? You memorized that e to the ax dx is equal to e to the ax over a plus c. Now you can see that a is 3 and it appears in the denominator as well and all of that stuff, right? You memorize this as a formula, but now you know where it comes from, right? And the same thing you memorized it for sine and memorized it for cosine and for other as well. So that is something that we have for this particular calculation. Now, obviously, this is going to become more involved, but just getting this idea, right, of transformation of going from x to u back to x, right, as in the final answer. The only reason why we are doing this is to obtain a simple integral which we can get in the chart of integral values. Now, obviously, u sub is not the end of the story. There is the entire chapter in your Calc 2 on integration techniques, where you learn integration by parts, partial fraction decomposition, trigonometric integration, trigonometric substitution. So there is much more to learn. But many of those techniques you learn in chapter 9 or chapter 8, sorry, in Calc 2 will end up transforming the integral so you can use u sub to go and solve the problem to the end. Let's take a look at another case of u sub. So let's say you have integral of 2x times cosine of x squared dx. So now we're getting into a little bit spicier situations. And in this case, right, you would say, all right, I know how to deal with the cosine separately. I know how to deal with 2x separately, but then there is multiplication between them. We do not have the rules for multiplication for integrals, only addition and subtraction. You remember that multiplication rules for derivatives had product rule, right? So you can't just do two separate things here. You also see that cosine is not cosine of x, but cosine of x squared. Now that's an issue as well. Right? Even if this wasn't here, I mean, first of all, this problem would not be possible. But second of all, right, this is not cosine x, it's cosine x squared. And that doesn't appear in the chart of basic values. So, right, some witchcraft has to be applied here, right, in order for this to be solved. And this is the first problem where I'm introducing the actual technique that I like to use, which is called function derivative pair. If you are able, in the problem, in the integral problem, to find function and its derivative, you are able, in that case, to set up your u sub. Now, for most people, right, function derivative, for most people, right, this is something that you would do in your head. You would say, looking at these functions and combinations of functions and all of this mess, do I have any one of these? And I have three functions here. I hope you guys see that I have 2x, that I have cosine of x, and then I have x squared. Because when I stick x squared into cosine x, it becomes cosine x squared. So when I decompose all of the function compositions, when I separate all of these functions apart from each other, what I get are these three functions that are all separate. And then when I have this, do I have on this list a pair where one of these is a function and its derivative with it? And sure we do. If I call x squared a function, its derivative is 2x. So being able to decompose all of the functions you see and then being able to find a function derivative pair, you see that cosine is not paired with anything, right? Derivative of cosine is negative sign, and negative sign is not present. That doesn't mean that it's never cosine, because in the next example I can make it so it cosine, right, is the function. But the thing is that your job is to, well, how many functions you have, sometimes 3, 4, 5, doesn't matter. Your job is to find the pair of the functions that work as a function and its derivative. And as soon as you're able to do that, the rest of the problem is a joke, because your u is always a function. And then you have your du over dx is equal to 2x, and then you ship your dx to the other side. Now, you don't have to solve for dx now, because look, 2 times dx, 2 times dx, that thing is du. So this immediately becomes cosine u du. Remember, u is x squared, and that's now switched, and then 2x times delta x is du. And all of that now is very simply, integral of cosine is positive sine of u plus c, and then we bring x back into the answer to provide the solution in the domain of x, because that's what it was asked of us to do. So this is what we have for this situation. So that's, and technically this is u sub. Now obviously it becomes much more than this going through, because some of the problems will involve trig identities. Some problems will involve separating stuff with square roots. And so there is a huge variety of problems, some algebraic manipulations before you can use u sub. Then we have to learn the back substitution. So this lecture has much more to offer. But if you are able to see this much for now, you are in a really good spot. Again, look for function derivative pair. And now that we were, dealing with trig, another very good question is the question that we can solve in two different ways using u sub to obtain obviously the same result. And that would be integral of sine 2x dx. Right, so this is a problem that can be done in two ways. And that will be sine 2x dx would be what? Well, let's go with the way one. I'm going to just use u substitution right off the bat. I will say, okay, u equals 2x, and then du over dx is equal to 2, from where du is equal to 2 dx. And from there, dx is equal to du over 2. So that's all what we have. Done, right? Plug everything inside. That's integral of sine, and then instead of 2x, I just have u, and instead of dx, I have du over 2. Now you know that the du is multiplied in, right? Because we did the theory that makes it into right, the rectangle. So du is like the width of it, so it's times. So you have the height times the width. So it's okay to be du over 2 because you're cutting the width of the rectangle, which is du. You're just cutting that in a half, right? So now this is du over 2. So this notation should not be weird. That's what I'm saying, right? It has physical ramification right here. So what you do is you just now kick 1/2 in front, and you have sine of u du, which is a basic integral, which is 1/2. Integral of sine is negative cosine of u plus c. Now this is further negative 1/2 cosine of 2x plus c. And that's it. Now you can write this as well this way, cosine 2x over 2 plus c, but they're both, you know, full credit answers. My MATLAB should recognize both of these answers as full credit, right? So no issue there. And as you can see, it was clear to us that this is something we don't want because of, you know, the I know thing that happens in your head. I know that the integral of sine of single x dx is negative cosine x plus c, and because that, you know, I know in your head, you say, okay, let me make this a single variable. And that's exactly what you did, right? You removed 2x and you put u instead of it, which actually makes immediately the u sub. And then this is the consequence that has to follow, because you can't swap x and not swap dx, right? That's not possible. You have to switch both. So this method, this u sub here, went through the problem, and as it went from one step to another, right, it followed that basic idea of u sub. But there is another way to do this problem, right? Same problem, integral of sine 2x dx, way 2. Well, this integral can be written as 2 times sine x cosine x dx. Aha! All I did is I used the identity, which we should all know from a trig course, right? So it says sine 2x is equal to 2 sine x cosine x. Like, this formula is one of the most basic formulas you get in your trig course. Aha! So now what is my function derivative pair? That's not a fire department, that's function derivative pair. Oh wait, derivative of sine is cosine. Ooh, so that's my sine x, that's my cosine x, because derivative of sine is cosine. Aha, I have function derivative pair, which means immediately I know that u is equal to sine x. Then the du dx, right, which is the derivative of sine is cosine x. Okay, that's good. That matches what I have up there under d. And then I just move my dx to the other side to solve for du. Ooh, this puppy here is the du. This puppy here is u. And I have this extra 2 and the integral sign. Oh, okay, well, that was easy. That's integral of 2u du. I mean, come on. Look at this, right? We went from a trig integral down to, can I just integrate like x? Oops. Which is in this case u. And the answer is hopefully yes, right? It's going to be u squared over 2 plus c. So the whole thing is just u squared plus c. And now you know that you are supposed to bring your value back into here, which is sine x. So sine squared x plus c. And you're done. There it is. That's the answer. So we did the entire problem, but this time, right, this time we used the identity to change the problem, which changed type of the u sub we're using to come up with the answer. Now you might say, well, hold on, that answer doesn't look anything like the answer I have above, right? You object, right? Well, it's very close to it. It's a very basic formula that, again, it's going to be one of the basic formulas to go into Calc 2 because of all the trig sections that you will have. If you guys remember power reducing identity, it says that sine squared x is 1 minus cosine 2x over 2. So this answer is actually 1 minus cosine 2x over 2, and then you can plus c, and then you can break it apart into two fractions, and then this 1/2 will be absorbed by c, and there you have it. Now, this move of absorbing values by plus c is something that you are not comfortable with yet, but eventually eventually you will be. Eventually you will be comfortable with it, and you will you will be solving these. Okay, so I gotta go get some. I gotta go get the bottle of water. I will leave you with the problem to enjoy by the time I come back. Let's go have x squared plus 1. Nah. Just x squared square root of 2x cubed plus 6 dx. So try this one, and I'll be back in a minute. So. Okay, hopefully you had some success with this function derivative. See, x cubed goes into 3x squared. Now, x cubed is attached to all of this other mess, so u equals 2x cubed plus 6, and a du is equal to 6x squared over dx over here. I'm used to immediately writing dx on this side, skipping that step of writing du over dx and moving dx, because you always do that. So I just write the dx on this side immediately. It's a differential. Okay, cool. I hope you see that this much is already present. So I need this 6. And there are two ways in which you can deal with that, right? One would be to divide both sides by 6, which is what we have been doing so far. So we could have said x squared dx is equal to du over 6, and then go and replace everything. I'll show you another way. So now I have square root of u, and then I have du over 6 instead of dx, x squared dx. So x squared dx is like a unit, right? It's x squared times dx, and that's what's underlined in orange, right? So that together replaced by du over 6. So now this problem becomes 1 over 6 integral u to the 1/2 du. And this is basic integral, right? It's basic integral because all you need to do now is to use the formula for integration, right? Plus 1, and you're done. So it's 1 over 6 u to the 3/2 divided by 3/2 plus c. And now we can cancel 6 and a 2 to get 1 over 9 u to the 3/2 plus c. Now remember, you cannot leave answer in terms of u, because no one cares about u, okay? We care about the x domain, right? Because the problem was posed in x. So you cannot leave it as u. And that it's just as simple as just, writing 2x cubed plus 6 to the 3/2 plus c. It's the same thing. It's just you're replacing u with what u is in terms of x. And that takes care of the situation. Ta-da! There it is. You don't believe me? Fine. Take the derivative of it. You must get this. This is why I always liked integration more than derivatives, even though integration is far harder than derivatives, much, much harder than derivatives, because you can check it, right? You get your answer, you box your answer, but then you say, is it? Right? And this is why it's very easy to score 100 on the integration exam. Because you can keep trying, unless you run out of time, obviously, but you keep trying until you figure this out. So we go and we say the derivative of this mess. And we just want to check, because we can. Oops. 3/2 plus c. Now, you don't actually have to write this plus c, because the derivative of that is 0 and just goes away, but whatever. So 1 over 9, then drop 3/2, and that's 2x cubed plus 6, and then that becomes 1/2, because it's minus 1, right? And then the derivative of the inside, which is the chain rule, which is 6x squared, and then plus 0 for the c. So you did have the chain rule, right? That's the chain rule kicking in. And now you say, all right, I have 3 times 6 is 18x squared over 9 times 2 is 18 times the square root of 2x cubed plus 6, and then 18 cancels 18. We're good to go. Immediately see that this solution for the integral was okay. Now, if you can't differentiate, if you can't differentiate, you shouldn't be able to solve the problem in the first place, right? Because there's differentiation here. So yeah, there's that part. But when you solve the integral, if you are interested in whether you did it correctly or not, you can differentiate, and that will be it. Here is another example. So it's going to be e to the x divided by 3e to the x plus 2 dx. So I'm just going to give you a few minutes or whatever to try work this out. Would anyone like to share u?
If I had to take a guess, I would say u is ex.
It's unfortunately no.
Well, then I'm wrong.
Can it be a? And then I would have to do W sub in that case. It could be, but then you have to do W sub. Would anyone like to suggest? Guys, it's okay to be wrong, you're learning. The worst thing you can do is stay silent, not try, and then get it wrong on the test, right? Working.
3e to the x plus 2.
There we go. So entire denominator turns out is this. Okay, so now what?
The derivative.
Good, which is du is equal to what?
3e to the x.
3 to the x and then dx. So we have to have that dx there in order for us to be able to replace it, right? Because dx needs to be replaced. So this dx has to be there. It's not there for decoration. Cool. Do I have 3e to the x on top? No, I don't. Now we can actually fix it. Look, I can put 3 out of nowhere and put 1/3 in front to balance it out. You're allowed to do that because 3 will cancel 3. But what happens now is if you put that 3, this is immediately your du and you don't have to flip things around in here. It's a technique, and if you don't like it, don't use it, right? You can just divide both sides by 3 over here and have e to the x dx, right? Which is the original one. So that's it. Now we have du over u. What is this integral? What is this integral?
Is it ln u?
Very close. Ln absolute u plus c. And you will be sick of this integral in Calc 2 and later differential equations. So this becomes 3e to the x plus 2 in absolute values plus c. There we go. All right. The question says, without having to solve the equation with both possible u values, how can we decide what the u value should be? Well, the first thing that pops to mind is always function derivative pair. That is the ultimate decider. If you are using that technique, you always know which one of these two would belong where. See, if I have a function derivative pair, the e to the x has the derivative as e to the x. Now, the trick is that the one in the denominator has a lot of mess. So we are going to, right, that one is the one with the plus 2. So we can, we will say u equals 3e to the x plus 2 because its derivative is 3e to the x, which we can fix like I did with this constant 3. Now, also, if you make a wrong choice, your problem either becomes worse, right? Impossible to solve, like it becomes worse, or you end up in a problem that has to be where you have to use, let's say, use substitution multiple times. So the suggestion of using e to the x to be u is still possible to solve the problem, but it will take longer, right? So if we take the same problem of e to the x over 3x, is it 3x or 2x? What I have? 3 to the, no, 3e to the x. 3e to the x plus 2 dx. And you say, let u be e to the x. And then in that case, du would be e to the x dx. Fine, but you will have to do one more substitution actually, because now what you get is a du over 3u plus 2. And when you look at this, it's not a basic integral, right? So you still have to do the substitution again. So let's go and say, all right, so how about now g equals 3u plus 2, in which case the dg is just 3 du. And this is where that 3 that we had before, right, is back now in the game. We can do 1/3 and a 3, right, to fix that. I should use a different color here because easier to see. There we go. And now when you do your substitution, you get 1/3 integral dg over g. And that's still 1/3 ln of absolute g plus c. Except now you have more to unwrap because you use 2u substitutions, and they can link. I mean, sometimes you will have to do this. Your g is 3u plus 2 plus c, and then you are now, instead you put e to the x, and you are back in the x domain, and it's exactly the same as the solution to the previous problem. So in some cases, your choice of u is still possible. It's just more work. And again, sometimes I have to just answer the question with its experience, right? Because if you, well, let's say you want to learn to lay tiles, like the tiles on the floor in the bathroom, let's say, and you're watching master do it, and everything is straight and perfect. And you just ask, well, how? How is everything so perfectly straight? And the only answer they can give you is experience. Like, they don't have superpowers. They don't have, extra 7 hands to hold things, right? It is the experience and careful methodical practice over years. And every question that you give me in this sense, how do you know, meaning how do I know? Well, obviously it's experience because I'm shoveling this 15 years, right? And you're looking at this for 15 minutes. There's a huge difference, right, in our approach to these problems. But again, with practice, right, when you sit down and you practice and you bleed over this, right, eventually you get to that stage. You just have to try. And when you mess it up, you try a different thing. And obviously, I mean, if you give up and say, this is stupid, I'm not going to need it, well, yeah, your education ends with Calc 1 because you will never pass Calc 2. That's clear. But those of you that really put time and effort and blood, sweat, and tears, I will say, into this, it will be okay. Now we are going to spend another hour next week. No, next week on Wednesday, in 2 days, right, talking about this. So we'll have many more problems for you to practice. It's time for us to take the integral of tangent x dx. So what should I do now? I know how much you love trig, so any ideas on how we should start this problem? Okay, yes.
Do you split tangent into a cosine and then sine?
Yes, that's exactly what YouTube said as well, YouTube chat. Very good. So we are going to write this as sine x over cosine x dx, and then we are going to use u equals, right, and then eventually du equals. So, so now we have what you call functional derivative pair. So now, what do we do with, which one do we pick as u? And you can't pick either. I understand the derivative of sine is cosine and derivative of cosine is negative sine. The issue over here that one is in the numerator and one is in denominator. So we can't pick either or. So let's just make a guess and see if it works or if it doesn't work.
Sine.
We are going to pick sine. Okay. So sine x and then derivative of sine is cosine x dx. That's a guess, right? Good. Let's go. Let's plug everything in. So replacing things, we start with the u divided by, oh, do we see the problem that in our problem it's dx over cosine x, and in my u substitution it's cosine x times dx? They don't work. They don't match. Like if I am to solve this for dx and plug in, I would actually get cosine squared there. It would make a lot of mess. Do you guys see that? That the problem has dx over cosine x and the u substitution has cosine times dx. And they're not the same. Which means that this choice doesn't work. The choice doesn't work because we did not get this, it doesn't fit. Over here you have dx divided by cosine. Because this is all times dx, so technically dx is with sine on top of the fraction, and you have dx over cosine. But your du is cosine times dx, so they don't match. So this is what I said, when you make a wrong choice, it's not a big deal. All you need to do is to flip it around. It's not the end of the world. So you say, okay, this is going to be then cosine x, and this is going to be negative sine x here. What do I have now? Well, I don't have negative sine, but that's very easy to fix by placing in two minus signs. They cancel each other. So one of those minus signs is going to survive on the other side. The other minus sign is going to be used for du, because you have the entire top be du, and the cosine on the bottom is just u. Now, what is this integral equal to? This is a basic integral. You should know this one from 4.9. Yes, with absolute values again. So ln absolute u plus c, and then we plug everything in there. Now look, we get negative ln of cosine x plus c, and we actually go and do more work. This looks like it's done, but it's actually not done. And the reason why it's not done is because tangent and cosine are not calculus pairs, right? Tangent needs to be paired with a secant. And luckily we have this negative to help us, because when that negative goes in as a power of the -1, this becomes ln, absolute value of cosine x to the power of -1, which is technically 1 over, so this is ln of 1 over cosine x plus c, which is ln of the secant x plus c. And that is our answer. So you see that the integral of tangent is not a basic integral. We had to go through hoops of u sub to solve integral of tangent. Now, do people go and memorize it as a formula? Yeah, they do, right? They go and memorize that as a formula. But again, you can also solve it and get your secant in there. I wonder if we can solve this in another way. This thing just popped into my head. Tangent and then secant, derivative tangent is secant squared. Huh. I'm just, as I was talking about the other stuff, I just realized that we can maybe multiply this problem by tangent over tangent and then use a different u sub to solve. I don't know, I've never tried this. I'm just trying this for the hell of it. So this will be tangent squared x over tangent x dx, and then we can use the Pythagorean identity here. Would that work? Pythagorean identity is 1 plus tangent squared x is secant squared x. Huh. Again, this is just a flex, okay? So this will be secant squared x minus 1 divided by tangent x. Oh yeah, this makes it much worse. But that's okay. I mean, it's still fun. Derivative of tangent is secant squared. So I have my u sub over here. If I separate now two fractions, see that? Dx, and then the separate integral, because we know we can separate integrals, you have 1 over tangent x dx, and that's actually the cotangent there. So you can also do the u sub on there. Wow. Okay, this is way worse, right, to solve the same problem, but it can be done. And then you'll have to probably go through whole spiel of another trig identities to put it back into the answer we have up there. But this is cotangent x dx, and now, right, use the same ideas. Well, I have to write it one more time because of the cotangent. I need to write that as a cosine over sine. There we go. The trig is so awesome. I mean, you can just do so much with trig, with these identities. And yes, this is the official way to solve the problem, easy and fast. But then there is this, which technically gives us the same thing. So over here, u is equal to tangent x, and then du is derivative of tangent is secant squared, which is exactly what I have on top. And the other substitution over here, g is equal to sine x now, because that's in denominator. And dg would be derivative of sine is cosine x, which is on top. So now when you plug this, you are working two separate substitutions, which will feed eventually back into the same problem. So now this one becomes du over u minus, and this one becomes dg over g. Oh man, this is ln of u minus ln of g. There we go. Plus c. And there we go. So ln of u, which is tangent x, minus ln of sine x, plus c. We know the formula for ln's. To put them together, it becomes ln of tangent x over sine x, plus c, which becomes ln of 1 over cosine only, because sine cancels sine, plus c, and there's your secant again. Wow, I've never done this before. It's just that's a lot of unnecessary calculations to get the same answer. But it's a flex, right? Because you have your Pythagorean identity there, then you have two different u subs, well, one is u, one is g, whatever. Then we had that notion that you can combine ln's, right, with the formula that we used before in your logarithmic differentiation. If you remember, the formula we used was, let's write it in red, whatever, that the ln of x over y is ln x minus ln y. Well, that's the formula I used just backwards, right? I used it this way to combine into a single ln, and when I combine it into a single ln, then tangent is sine x over cosine x, all of that divided by sine x over 1. And when sines cancel, you just get 1 over cosine, and 1 over cosine is secant. So it's a lot of cool identities and things, but it's definitely overkill to solve the problem that you can directly solve by sine cosine up there. And we use two u subs as well. So kind of cool. This is where I want to end today with the 5.5 u sub. The homework will open for you to practice between today and obviously Wednesday, but we are going to have another u sub session, right? Like a part 2, the revenge of u sub, where we're going to see back substitution and we're going to see double substitutions, like the nested ones maybe, and things like that, because those are still around. And as I said, right, this is the most important integration technique going into Calc 2. So we really need to spend some good time. We're going to take a break. And when we come back from the break, we are going to talk about the upcoming exam this weekend. So we'll do the exam 3 review. So let's go into the music mode.